basically means what you think it does. So, such that if we look at any homogeneous depth-5 circuit, computing PD, it will have size something like 2 to the omega square root d. Okay. So this will be over Fq, Q being over 4. And these polynomials in fact will have 0, 1 coefficients. So these are polynomials with multilinear homogeneous polynomials of degree d with 0, 1 coefficients. If we want to compute them over small fields by a depth-5 circuit, we would need a really large size.
So this is for the computation of the polynomial or the function?
Good. No, it will be for the polynomial, yes. And this family of polynomials will be in V and P. That's what I mean by things being explicit. So that's the notion of explicitness.
What's the degree?
The degree will be d. So I'm indexing, yeah, and it will be.
What is the m after c?
There's just n is about d cube. Yeah. Okay, so is the statement all right? Okay, so yeah, so I want to make this this difference clear over here. So.
If this was for depth-6, you would not be done because this d is not n.
No, so okay, good. So
comparing to the other
yes. So Agrawal-Vinay says that for depth-6 we'll need a lower bound of n to the d to the 1/3. So if we have exponential in little omega log n, then we would be done. And this would work.
Yeah. You want
Yes.
to stress it.
Yes.
This is just for homogeneous, right? And
Yes. So everything will talk.
non-homogeneous to get certain lower bound.
No. So it's enough to prove strong enough lower bounds for depth-4 circuits which are homogeneous, have bounded bottom fan-in and stuff like that. Like really structured circuits. That suffices.
But if you get something for the homogeneous case, then it will good enough something for the
Yes, then it would.
give you general
Yes.
lower bounds.
Yes.
Because you can homogenize.
Right. So if you have big circuits, you can homogenize them. So
Okay, at what cost?
at poly d, comma n, like d square or something. We don't know how to do these homogenizations when the depth is small though. And that's why in many of these, for depth-3 circuits for instance, we know homogeneous lower bounds, but we don't know non-homogeneous lower bounds. And as Avi pointed out, there's a big difference between the computational power of these things.
So what about this question if the polynomial or the function? So the function
So I'm going to talk about it. And this is something that we'll use in the proof. So when we are talking about, so far we were talking about circuits computing polynomials. I mean computing polynomials as a formal object, meaning that when you expand out the circuit, write it down as a sum of monomials, it should look like the polynomial that I give you. So that notion is, so this is called syntactic computation. And the lower bound here is for syntactic computation. But there are parts of the lower bound which work, which are functional in some sense. So to contrast this, with functional computation, where if you have an arithmetic circuit over a field Fq in n variables, I can think of it as a function from Fq to the n to Fq, right, in the natural way. So I'll think of this n tuple as an evaluation of as a setting of values of the variables. So if a circuit is computing a polynomial syntactically, then it's also computing it functionally. But the vice versa is not true.
For example, the polynomial x to the q minus x.
Right, x square minus x over f2, for instance. This is the zero function, but it's a non-zero polynomial. Okay, so
What do we need for this to work?
we'll just need syntactic computation.
And then we get syntactic lower bound.
Yes, yes.
So the only thing missing is that we are doing for the 5 instead of 6. So what
Ah.
missing?
Yes. So even that's not missing. The thing missing is that we are so depth-5 circuits. So in particular, if we can prove lower bounds of this type over, say, reals, for this model, it would suffice for a result of that type. So it would suffice to prove general circuit lower bounds. So over reals, we know that arithmetic circuits have a better depth reduction to depth 5 than depth 4, for instance. But over small fields, we don't know how to make these techniques work. So over small fields, yeah, if we had proved it for depth 6 and the bound, any bound which is better than this is definitely better, would have.
What do we need to be for depth 4?
So we'll need exponential in omega d to the 1/2 log n. This is what you would need to get in order to imply general circuit lower bounds. But if you have a big omega here, then we know how to prove these bounds. Okay. Good. So I want to talk about the proof. Okay. So almost all the results that I sort of mentioned over there, the proofs have a certain structure to them. So the proof basically looks like this. So in the first step, we define a function. So define a measure, which is a function from polynomials to natural numbers. So think of phi of a particular polynomial as a measure of its complexity in some sense, intuitively. Okay, and then we'll prove that small depth-5 circuits have a small value of phi. And then we'll prove that so the polynomial p sub d, if we look at phi of that, that's large. Okay, so hopefully I'll get to at least sketch these two things. And this will believe. Okay, so the depth 3 proof of Nisan-Wigderson, the depth 4 proofs, all of them look like this. What changes is what is this phi, what's the function, and the complexity of these parts change accordingly. So how hard it's to show things here. Okay, so let me try to define phi. Okay, so it's based on the following two observations. So what's a depth 5 circuit? It's a sum of product of depth 3 circuits. Right? And how does this differ from a depth 4 circuit? So a depth 4 circuit was the sum of product of sparse polynomials. If the size of the circuit is small, these polynomials have very few monomials. So a natural thing to try would be to start with a depth 5 circuit, and we know depth 4 lower bounds. So somehow reduce the depth 5 case to the depth 4 case, and then lower bounds here will potentially imply lower bounds here. But the problem is that, so if we look at a gate here, so at the bottom two levels, it's a product of linear forms. Right? And if we want to expand it as a sum of monomials, then the sparsity blows up. So the size of the circuit becomes really large. So take, for instance, your Q being sum over I xi from 1 to n to the d. If I want to write this as a sum of monomials, then I'm going to use all possible monomials of a certain degree. That's too large to get here. But it so happens that if the bottom fan-in, then a transformation like this does indeed work. And so I mentioned these lower bounds for depth-5 circuits with bounded bottom fan-in. They basically, in spirit, work like this. You start with a depth-5 circuit, you reduce it to depth-4, and then hope that the depth-4, your reduction has been economical enough for the depth-4 lower bounds to kick in. Okay. Okay, so since here when the bottom fan-in is unbounded, it seems hard to do that. So we wanted to understand these product of linear forms better and try to use that in some way, some non-trivial way. So okay, so let's fix some notation. So let's say Q is something like L1, L2, L sub t. So these are all linear forms. This is a product of t linear forms. And let's say that the rank of L1, Lt is some R.
T
So
is
the
large anyway. We think of T as large now.
Yes, we'll think of T as large, yes. And let's say that the rank of these linear forms is R. So there are R linearly independent linear forms here. Without loss of generality, let me write it as Q equals L1, L2, blah, 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 up to LR, and then some other stuff. And these are all linearly independent.
This smells like Grigoriev-Razborov.
Yes, right. So, okay. So this is an observation of Grigoriev-Razborov, Grigoriev-Karpinski. So there are two observations. So if I evaluate Q at a random x in Fq to the n, then the probability that it's non-zero is at most 1 minus 1 over Q to the R. Okay, where R is the rank. So why is this true? So we are evaluating Q at a random x. So let's look at L1. L1 is a non-trivial linear form. We are evaluating it at a random x. What's the probability that it will evaluate to 0? 1 minus 1 over Q. Similarly, what's the probability that L2 is going to evaluate to 0? 1 minus 1 over Q. And since they are all linearly independent, these events are independent. So the probability that Q evaluates to 0 is to something non-zero is at most this. Okay, so this is one observation. The other is, yeah, I mean, this is again, so there is a polynomial f, degree of f being at most q minus 1 times r, such that for all x in Fq to the n, q of x equals f of x. Okay, so why is this true? Well, Q was a product of linear forms. L1 to LR are the maximal linearly independent subset. So everything else is a linear combination of these things. So in particular, it's a function of these things. So let's expand the whole thing out. We are working over Fq. So L to the Q is of x is equal to L of x for all x. Right, so this is as a function. So this is equality. Right, so in particular, we can assume that we can go mod the ideal generated by objects like these. So the individual degree of each of the LIs will be at most q minus 1. And there are r of them, so it's at most q minus 1 times r of them. Is this okay? So we'll have to come back to these things, but let's see what they give us.
Can you explain this again?
Yes.
Second observation?
The second one, yeah. So I can write, so L1 to LR are the maximal linearly independent subsets.
So when
Yeah.
I'm here, now we're claiming that there is a polynomial of smaller degree that is equals to
The degree in, the original degree there is t. He wants to get something that depends only on the length and the size of the t. T may be n, I don't know.
Yeah.
But r may be much smaller.
Okay, so it's not clear whether f has degree larger or smaller.
Right, good. So that's because I haven't told you what R I'm thinking of. I'm going to think of R being roughly square root D. Remember, D was the degree of the polynomial we were computing. So in particular, T could be as large as D. But Q is a constant, so Q times R will be at most square root D. And
So
yeah, you do get,
the
yes,
degree of the
yeah,
polynomial
yes.
somehow.
yes.
It's a dichotomy. These two observations are serve for a dichotomy. You say r is either big or small. I don't know. If it's big, then when I hit it with the random restriction, I'm going to make it 0.
Okay.
If r is small, I can approximate it at least as a function. I can compute it at least as a function in much lower degree than it was.
Right.
Nice.
Okay. So one more thing which I want to say here. So what is Q? Q is a product of linear form. So it's one of these gates at this level. This probability, so the probability that at a random x Q evaluates to non-zero is this. The probability that there is some gate of rank at least R which evaluates to non-zero by a union bound will be something like the size of the circuit times this quantity. Right?
So this is the middle sigma?
No, this is, so I'm looking at product of linear forms which appear in the circuit,
Yes.
and I'm going to union bound over them.
Oh.
And all the product of linear forms which are of high rank. So the probability will be at most the size of the circuit times 1 minus 1 over q to the r. Think of r as being something like epsilon square root d. So if the size of the circuit is 2 to the epsilon prime square root d, then this quantity again, so this probability will be at most exponential in negative epsilon square root d, right, where all epsilons are different. So in particular, all the high rank gates in the circuit will evaluate to 0 at a random point. All the low rank product of linear forms are low degree polynomials as functions.
Variables. I mean, if you have, the standard argument, if you have only
Yeah.
one variable, but if you have no.
Oh no.
The degree of
This is multivariate.
I mean, even if you have let's say you have the product of one of these.
So
N is a.
yeah, n is a number.
Sum.
Yeah, you might as well think of the LIs, the first RLIs, as different variables,
Right.
x1, x2, up to xr. And the rest of the other stuff are
Polynomials
they
in
are
them.
forms in this same values. Just change of basis.
Right. Very good. Okay. Okay, so those two observations already gave us something very interesting.
It shows that you can approximate your
Right.
by,
Right. So what just happened was, so if we had a C which was a depth 5 circuit, of size something like 2 to the 4 root d, then so there exists a circuit C prime,
Yeah, this may be little or 40 or something.
epsilon root d for a small enough epsilon. So there exists a circuit C prime which is a depth 4 circuit such that, so first of all, size of C prime is going to be at most the size of C, Okay, good. So this is not really true. So what's true is it's going to be at most n to the O of okay. So let's
Would be a little smaller than would be, right?
yeah.
Would be like
Yeah, we can take it something smaller, right? Yeah. So do I want to say it precisely? Maybe not. So I'm not going to say things about the size, and I'm not going to say things about the size here either. So if C was a depth 5 circuit of not too large size, then those two observations together say that there is a depth 4 circuit whose bottom fan-in is small. It came out to be Q times root D, but let me just write T here. Okay, such that probability over a random x in Fq to the n, C prime of x equals C of x is really large. Okay, why does this follow from there? Well, you look at C, look at all the product of linear forms which appear here. They are either of high rank or they are of low rank. If they are of high rank, then we know that they can be approximated by the 0 function because they are 0 on 1 minus little of 1 fraction of points. So let's replace them by 0. So then all you are left with is these product of linear forms which have low rank. But then we know that there is a low degree polynomial which agrees with this product of linear forms everywhere. So let's replace this product by the low degree polynomial. And we'll write the low degree polynomial as in its monomial representation. So then we can combine the summations to get a depth 4 circuit with small bottom fan.
So you can say that the first two layers did not change.
Yeah, they did not change.
The size exploded on the third layer.
Right.
Maybe you
Right.
can care about it.
Yeah. Right. Yeah, so that's why I didn't want to write it. So for circuits like these, we know really strong low bounds on the top fan-in, which did not change in this transformation. So that's why I didn't.
But not for the functional.
Yes, we don't know that for functional things, right?
You're talking, you now move to a functional.
Yes, but I'll go back.
Yeah.
So this is an observation. What this implies is that if we can prove functional lower bounds in a very strong, in the sense of approximating things for depth 4 circuits with bounded bottom fan-in, then we'll have depth 5 lower bounds.
So what is this? What is this thing?
Q minus 1 times.
T is roughly q minus 1 times square root D or something, based on what R I pick. Okay, so it's something small, non-trivially small. So this was an observation, and we were stuck here for a long time. I don't know how to prove this. But I really think it's a nice question. The reason I think it seems to be difficult is the following. So all the small depth low bounds that I talked about, that I mentioned, all of them are based on these what are called methods of partial derivatives. So you take the circuit, you take the polynomial, you look at their partial derivatives, you compare the dimensions, you do some stuff with partial derivatives. But yeah, partial derivatives don't, so this is very vague, but partial derivatives in some sense capture the structure of high multiplicity zeros of a polynomial. Over here, all we are saying is that functionally the two circuits are the same. They compute the same function on most of the points. It's not really telling you much about higher multiplicity zeros. Okay, so if that was vague, so let me give you an example. So consider the polynomial q, which is the monomial x1, x2, blah blah blah, xn. Okay. If we look at the partial derivatives of it, and these are the formal derivatives, so in the sense of derivatives. So partial derivatives, so if we take a derivative with respect to x1, we are going to get the rest of it. We take a derivative with respect to x2, we are going to get the rest of it. So if we look at the partial derivatives and we look at the span of them, so the span is 2 to the n. All possible subsets will appear. Now let's say we are working over f2. And let's look at the constant function 0. This function and this q agree everywhere except for one point, which is the all ones point. Right? But 0 is a really simple function. This has a very large partial derivative span. So in some sense, partial derivatives don't behave well with this kind of.
Okay, so this was a lemma
Yeah, and it followed.
from this.
Yes.
And now, what do we need?
We
Good.
don't have lower bounds like
We would want to prove these lower bounds, but
Oh, you have this for, okay, I see.
so I would want to say that now we'll prove this lower bound and we'll be done, but I can't say that because I don't know how to prove it.
Just because the 1 minus the log 1?
No, because of the fact that this agreement is,
Almost.
No, because it's function.
it's function.
It's functions. All the lower bounds in arithmetic circuit complexity are on the syntactic computation of polynomials. Or almost.
Yeah.
Seems to be
Okay, so we don't have,
yeah.
the techniques don't talk about this.
Okay, so
case.
the lower bound for depth 4 with bounded.
Yeah, they are just for
Yeah.
syntactic.
For syntactic,
Yeah.
and
Yeah.
we need something functional now?
Yes.
That's what he reduced.
Yes.
The reduction was function.
We would want to say, so what is syntactic saying? It's saying that if a circuit is going to compute exactly your same polynomial, then the size has to be large. We would want to say that if the circuit agrees with your polynomial on all the points of Fq to then also the size has to be
You may
large.
compute like a different polynomial.
Yes, but as a function on this,
So now what's the connection to that?
so there's no connection. This is really why I think this problem is hard. So look at the polynomial Q.
I understand this point, but I don't
Yeah.
understand the connection.
Good. Okay. So let me.
Oh, okay.
The connection is that as a function it's easy and as a polynomial it's hard from the point of view of the standard measure of difficulty. In arithmetic circuit complexity, the standard measure is the dimension of the span of partial derivatives. The zero function, this measure is 0. In the monomial, this measure is 2 to the n.
But where is the functional versus?
So as polynomials,
It's the zero.
there's a huge gap between the
Oh,
complexity
I see.
measure. As functions, they differ
Oh, I
only
see,
in
I
one
see.
point. They are
Right.
very close to each other.
Okay.
Something it doesn't match.
Okay. So anyway, good. So we'll have to do something different. Yeah, I still like this question. I don't know how to solve it.
You can go over time enough, don't worry.
Okay.
That's interesting.
So what we need is this observation 1.1.
It's also partial derivative.
Yes. So we were looking at Q, which is a product of R linearly independent linear forms and some other stuff. That observation 1 is saying that at a random point it evaluates to 0 with a really high probability. Okay. I also want to say that not only does Q evaluate to 0, very, very high order partial derivatives of Q will also evaluate to 0 with a high probability. So let's see why this is true and then probably state it formally. Okay, good. So let's see it here.
Because each one there
Right.
reduces the rank by 1.
Right. So if we look at L1, the probability that L1 of x is 0 is 1 over Q, and these events are independent. So each of these guys vanish with a probability 1 over Q. So in expectation, R over Q of them will be 0 at a random point. Right? And then these events are independent because LIs are linearly independent. So by Chernoff, we'll expect like 1 minus epsilon times R over Q to be of them to be 0 at a random point. So in particular, so if now look at Q, take an x where these many of them are 0. If you look at partial derivatives of Q up to this order, all of them will also vanish because each of the terms will contain something which is one linear form which is 0. So good. So I want to say that probability over x, the multiplicity of Q at x is less than 1 minus epsilon times R over Q is small. Right, and what does this mean? Well, by multiplicity I just mean that partial derivatives of Q up to order this will also vanish at this point x. Okay, so this polynomials. So this again is an observation which is used in one of these papers. Okay, so are we good with this?
What do you mean? They use
I think
multiplicity?
at least Grigoriev-Karpinski can be thought of in this way. Okay, so this is 1.1. So there's an observation 2.1, which just says that if the observation initially was that if the rank of linear forms feeding into Q is R, then it's a degree Q minus 1 R polynomial as a function. But this observation will also be true for all its partial derivatives, right? Because if Q is a product of linear forms of rank R, you take derivatives of it, they are also going to be product of, so they're going to be a sum of products, and each of the product terms will have rank at most R. So all partial derivatives of Q are also functions of degree less than equal to Q minus 1 times R. Okay, in fact better, I mean depending on what order derivatives we take. Are we good? Okay, so these are the two observations we are finally going to use. Remember, what we were trying to do was to define this function phi. Okay, so at this point, so what do we know? So we know that if we have a small depth-5 circuit, let's look at product of linear forms present in the circuit. If it's of high rank, then it's going to vanish with really high multiplicity almost everywhere in Fq to the n. And if it's of low rank, then it's really of a low degree. It's really a low degree polynomial in disguise. Okay, so I'm not sure how so I'm going to define phi now. I'm not sure how intuitive the connection is going to be, but this was why the fact that we are going to look at these guarantees, this observation 1.1 and 2.1 are with respect to evaluations and not the polynomial itself, really motivated the definition of phi. So let me define it. So let's call it evaluations of shifted partial derivatives. Okay, and we'll index it by three things. There will be two parameters k and l, and there will be a set S of Fq to the n. Okay, so it's going to be a dimension of a linear space, and I'm going to define the linear space as in the following way. So we are looking at phi of p. Okay, so first step I'm going to do, so take all partial derivatives of p of order k. You can think of order equal to k, order less than equal to k, it does not make much difference. Okay, so let me denote this set by okay, now we construct this new set, which I'm going to denote as follows. Yeah, okay, so this is a bad notation, but what it is really is that you look at all these derivatives that you have constructed and take those derivatives and multiply them by monomials of degree L. So x to the alpha times r, where r is a kth order derivative of p, and so x to the alpha has degree equal to L. So we take the derivatives, we multiply them by monomials of degree L, like all monomials. We generate a larger set of polynomials.
Yeah, so x again is this all the variables.
Yes, x is all the variable set.
Okay, so what are the parameters here?
Ah,
That is what?
It's complicated, the choice of parameters. L,
Yes.
for example, will be much larger than n.
no, it won't be
But
here.
Not for you.
No, it won't
for
be. So
you.
L is going to be roughly n over 2.
Okay. For you, you don't need.
Right.
But sometimes just to get, I mean, so this has been standard the last, I don't know, 5-6 years to use this XL delta K as a progress measure, and that has generated all these wonderful lower bounds. But sometimes it's the choice is not, the choice has to be sometimes extremely careful. It's not clear even
Right.
completely why, and sometimes this L needs to be much larger.
Yeah, sometimes L is larger, but here you should think of L being as roughly n over 2,
And K?
K being roughly square root d.
Oh wait, but it's much larger than the degree.
It's much larger than the degree, yeah.
So it's much larger. It's like cubic in the degree.
Right.
So
It's yeah. It's much larger than the degree, but it's small compared to number of variables. Okay, so this is a space. So I'm not going to go into why this is a nice space to look at, but there's some intuition into why these spaces are nice. So now we are going to look at the vectors
You take everything spanned by that.
Yeah, we will. So these are polynomials. Now I want to look at their evaluations, their truth tables on S.
This will be the set of places where it's correct.
Yes.
Right? It's almost all.
Yes.
It's almost all the space.
It's almost everything, yes. We'll have to choose S carefully for the proofs to work out, but intuitively, yes. So is this fine? So we look at derivatives, we look at all the shifted derivatives, and then we evaluate the shifted derivatives on this set S. And this is a vector, it's a long vector. And then we are going to look at the dimension of the linear span of these guys. Okay, so phi of P is defined as the dimension of the FQ span of vectors in step 3.
So if you, in the previous proofs you took S to be the whole field, you evaluated this is your progress measure as opposed to the dimension of formal polynomials. Would it work also or not? I know the original Kayal or the.
Yes, so
Will it work?
some of it will, but some of it won't. So the proofs for depth 4 lower bounds will work, like can be made to work, which we have to do that in this proof. So that we know will work, but the other ones won't.
So your paper with Shubangi will
Yeah,
work,
so a part of it will work. So the part where we proved low bounds for the polynomial in VNP, we can make it work. VP, I'm not sure. Yeah, but all of it should work.
So what's new here? It's 3 is new? Evaluating on S is new? Why is this measure different than the other measures?
Why is this different? Well, evaluation is different. But you can think of the earlier measures, you could think of S as being 0, 1 to the n, and then the earlier measures also will behave like this. But
If you take all 0 to the
yeah, so
There was no real need to consider this step 3. I mean, what most papers work with was the dimension of the span of this space in 2, just a space of formal polynomial.
Okay, and somehow 3 is it helping us with the x1 to
it's helping us here because of these observations. I mean, okay, intuitively what these observations are telling you is that there is a large of the domain Fq to the n where your circuit is simpler in some sense. In what sense? Well, all the high rank gates vanish with high multiplicity. In order to use this, you have to look at evaluations. It's not clear how to look at the polynomial and use this. So that was why we wanted to look at evaluations.
Reduction was functional, so some
Yeah,
of the
so-
syntactic measures just don't work.
Yeah, they don't seem to
Talk
capture.
about this.
Yeah.
I understand, but there was this example with the polynomial
Yes.
Yeah.
Yes.
How would this measure be better?
Good.
Yeah, if it's 6.
Yes. So we'll get to it. So we'll prove something.
The point is that S is all but the 0 point, right?
Right.
Then
Right. So if S was everything but except 0, then the complexity of the polynomial is large, right? But 0 has a small complexity, so they can't compute each other.
once you disallow the 0 point, you cannot approximate the monomial by a simple.
So I would have chosen S to be all of F2 to the n except
This side.
the all ones point or something.
So you can exclude.
Yes. So an appropriate choice of S will let you contrast the circuit and the polynomial. Okay. So this is a measure. If you haven't seen this before, it will look strange why you do this, but it seems to work, and there's reason for doing this. Okay. Good. So now we have the measure. So we have step 1. So I haven't told you what. So K will be roughly square root D. L will be roughly n over 2, slightly smaller than that. S. So think of S as being a subset of points where all the high rank gates vanish. We know that we can take S to be really large, like 1 minus little of 1 times q to the n. But S, we'll end up taking S to be. So S will be a subset of C plus 0 1 to the n for some C in Fq to the n. So what does this mean? It's at the hypercube and you take a random translation of it.
Although you can probably take something much bigger.
Yes, but we don't know how to. I don't know how to make like the proof work for things much bigger, and there's a sort of a technical reason for it. So this S is what we work with. Yeah. So C is just a technicality. I would really like to make this proof work with S being 0 1 to the n, but then 0 1 to the n might lie in the error set, right? It might be the set of points where the high rank gates do not vanish, in which case that won't work. But a random. Right. So you work with a random translation of it.
But why you wanted to work with S equals 0 1 to the n?
Obviously, you have to calculate this.
That's one reason. The other reason is that when we have to bound this for the polynomial, we'll have to look at a matrix, and we'll have to bound the rank of the matrix. And the way we'll bound that will be we'll factorize the matrix and bound the rank of each one of them. There, if the sizes are very skewed, then we don't know how to get good bounds. So we'll need the size of the set S to be small. So I'll come to it in a minute.
Well,
Yes.
so I mean, in terms of this, choosing this point of C, I mean,
Yeah.
the class you're considering is closed under affine shifts.
Yeah.
So, I mean, can
Yeah.
you use some sort of like random self-reducibility?
Yes. So that's something that will happen in the proof, but I think you can do something like that. You're right. Yeah, I think that might simplify things a bit. Okay, good. So we have the measure. Now we have to upper bound it. We have to show that all small circuits have a small value of this measure, and then construct a polynomial which has a large value of the measure. So let's do step 2, which is upper bound on phi of C if the size of C is less than or equal to, let's say, root D over million. Okay, so so lemma so phi of C is going to be less than or equal to the size of C times something like D plus K choose K times N choose L plus something. some poly n. Okay, so this will be some quantity. This is not the optimal, but it's much cleaner to prove this. Okay, so the terms will start making sense if they don't right now. So the first observation is that phi is a linear function. So it's a sublinear map. So in particular, if you look at two polynomials p1 and p2, so phi of p1 plus p2 will be at most phi of p1 plus phi of p2. Why is this true? Well, remember how phi was defined. We took derivatives, which is a linear operation. We multiplied it by monomials, which is again linear operation, and then we were looking at evaluations of these things. And then we took the dimension of the linear span, so everything was linear. So phi will be sublinear after taking a sum. So this means that if we are looking at phi of a depth-5 circuit, which is really a sum of product of depth-3 circuits, something like this. So this summation, so I can say that this is at most the size of the circuit times the upper bound on one of these terms, right? So okay, so this is really bad notation, but is it clear what I mean? Okay. So I want that.